Lecture 10 is going to talk about the expectation, variance, and probability distribution. So we're talking about the expectation and variance of our random variable x. So the expected value is denoted by E of capital X or mu of x, and it's also known as expectation or mean. So by definition, so remember last time we talked about PDF of our random variables. So basically if we had a PDF f, if we can write our CDF, our cumulative distribution function, or our probability that capital X was less than or equal to x, as this integral from negative infinity to little x of some probability density function here. So our expectation or our mean is just a weighted average. So here we're looking at the integral over our whole entire real line. Remember our random variable is a mapping from some sample space to our real line, so we're looking at the integral over our entire real line of our probability density function f multiplied by our values x, so weighted average. So remember for our discrete random variables, we can think about, instead of probability density function, we can think about the probability mass function. With discrete random variables, we have a finite range. So here A is a countable set here, and it could be infinite. I said finite. It's countable. So it's a countable range, A sub I. So to get the expected value or our mean, we sum up, again, this is our weight. We weight our probability mass function at A sub I by the value A sub I. If we have a combination, so if we have a random variable u of capital X, then our expected value of our u of x is simply just putting u of x in for the weights in both of our expressions that we had on the previous slide. And expectation is a linear operator, so if we have a constant times our u1 plus a constant times our u2, and we want to take the expected value of that, it's the same as if we take these constants out and take the expected value of u1, expected value of u2, and then take the linear combination. So our variance for our random variable x is denoted by sigma squared. You might see also sigma sub x squared. The sigma sub x just allows you to realize that you're linking that sigma to the random variable x. Or you sometimes see var of x. And it's just defined as taking our random variable x minus our mean, that squared, and then taking the expectation of that. So a formula for that, we're going to derive a formula for that. So our variance of our random variable, if we look at this quantity, we can multiply this out. We can get our random variable squared minus 2 times our mean times our random variable minus our mean. But remember, our expectation is a linear operator, so we can split this apart. The mean here is just a constant, so it comes out. So here we have the expectation or mean of our x squared. Our e of x is just mu of x, so here we have minus 2 mu x squared plus mu x squared, so we get this minus mu x squared. So as an example, let's suppose that x is a random variable and it's a discrete random variable with a uniform distribution. The discrete uniform distribution has the probability mass function, which is defined by this, and we're going to go over some of the distributions, more common distributions, at the end of this video. So this is the formula for probability mass function for a discrete uniform distribution. So now we want to find the mean and the variance. So here we have 1 over n, where x takes on the finite values 1, 2, all the way up to n. So recall that for a discrete random variable, we can think about our mean as having this weight here. So this is our probability mass function evaluated at the value, and these are our values. So when we're looking at mu of x, we're going to have x times 1 over n, because 1 over n, let's go back, is our f. So we put this in for our f, it's 1 over n. We have our x, We can bring out the 1 over n. The summation is x goes from 1 to infinity of x. Remember, this can just be written as n times n plus 1 over 2. The n's cancel and we just get the mean is n plus 1 over 2 for this random variable x. This satisfies the uniform distribution. The variance, the formula for the variance we have was e of x squared minus mu of x squared. Our mu of x was n plus 1 over 2, so we're going to substitute that in. Let's first find this e of x squared. E of x squared, we're going to be putting in x squared here. The 1 over n stays the same. We're looking at the sum. As x goes to 1 to infinity of x squared, we can write that sum in a finite form as this. The n's cancel. Here we get e of x squared. So to find our sigma squared, we just want to take that value and subtract off our mean. So here's that value minus our mean. So we get n squared minus 1 over 12 for our variance of a discrete random variable x, given the uniform that satisfies, has the probability mass function for a uniform distribution. So another example, let's x be a continuous function this time, with a uniform distribution on the interval 0, 1. So in general, if you, the PDF for a uniform distribution on the interval a to b is defined as 1 over b minus a whenever x is on that interval a to b and 0 otherwise. So when we want to find the expectation here, we're looking at the expected value, so we're integrating over our entire real line. We have our weight here, our x times our f of x. Remember, our f of x is, we're looking at the interval 0 to 1, so it was 1 over b minus a, so we have 1 over 1 minus 0, which just gives us the interval x on the 0 to 1 because we're only looking on the interval 0 to 1, so we just get 1/2. We're looking for the variance. We're going to take our e of x squared minus our mean. Here our mean was 1/2, so we're going to have 1/2 squared here. Our expectation for x squared, we have the x squared here. Remember again, this was the 1 over 1 minus 0, which is right here. So we get 1/12. Next example, suppose we have a game consists of tossing a die, and you receive a payoff, capital X, which is a random variable, equal to n dollars if you have n pips on the die. So it's natural to define the price to play one round of the game as being the expected value of X. If you could play for less than the expected value, then you're sure to make a profit as long as you go long enough. Because remember what the expected value means. It's the mean, the likely that you would get if you play long enough. That's the average of what you're expected to get. If you play more, if you end up paying more than the expected value, then in the long run you're probably going to lose money. So let's think about what is this this payoff. So X is a discrete variable. We're talking about it having range 1, 2, 3, 4, 5, 6 because here is the number of pips that show when you toss a die. So the range is 1, 2, 3, 4, 5, 6. The expected value, so our probability mass function for each one of these is just 1/6. So here we have the 1/6. Here we have our weight. So we can write this, our sum of I, so we're going to have 6 times 7 over 2. 6's cancel, we get 7/2, so we get $3.50 is the expected value using the discrete uniform distribution again. And if I can play for, let's say, $3 and I plan to play for long enough, then I expect to actually make profit. If I pay let's say $4, then I would expect to lose money along the way. Okay, suppose that you have a waiting time to be served at the post office at a particular time of day and particular location. Let's suppose that you know that it's going to follow an exponential distribution with parameter lambda equals 6. So first of all, I got to tell you what the exponential distribution is. This is the formula for an exponential distribution given parameter lambda. So we want to know what is the expected wait time. So this is continuous distribution. To find the expected wait time, I'm going to integrate My f is 0 for x less than 0, so I can look at just going from 0 to infinity. This is my f, so I have lambda e to the minus lambda t. Here I'm thinking about time, so I changed everything to t. And here's my weight t. So I look at the limit as a goes to infinity. I take this integral from 0 to a. I can use separation of variables here and solve, and I get that my expected wait time is 1 over lambda. So if I look at lambda being 6, the expected wait time is 1/6 per hour, or 10 minutes at the post office. Okay, so I promised you some distributions. You've already seen the discrete distribution. So this was the f of x is 1 over b minus a, x between a and b, and 0 otherwise. Geometric distribution, this is thought to be the probability of success in x plus 1 trials, where p is the probability of its success. So here, p is the probability of success. You're assuming x plus 1 trials, and here's your x. You have a binomial distribution. This is similar to the previous, the geometric. So the binomial distribution has notation b of np. It's thought to be the probability of x successes in n trials, where p is the probability of success. Here, n is some positive integer, and just reminding that n choose x has this formula. Again, some more discrete distributions. We have the negative binomial, which is the probability of n successes in n plus x trials. Well, p is the probability of success. If you have n is equal to 1, then this is the geometric distribution. Poisson is normally used when you actually want to count the number of events happening during some time interval. So the formula for the Poisson, it has parameter lambda. Lambda has to be positive. So f of x is given by this for parameter lambda. Continuous distribution, so now moving from discrete to continuous, we also have a uniform distribution for continuous function. This is what we already seen. This is normally what random number generators use a lot, and it's used a lot in stochastic models. Gamma distribution is used, it's normally associated with waiting times, the time until one or more event occurs. So here, this is the formula for capital gamma. Alpha and beta are constants, and gamma has this nice form whenever alpha is some kind of integer. And again, I'm just running through these distributions because these are ones that I don't expect you to remember. They're ones that I expect that you can look up eventually. So I just want you to know that they do exist. So here, exponential distribution, again, it's associated with waiting times, and it's actually used a lot in continuous Markov chain models to figure out the time to the next event. And then you have your normal, which most everybody knows is the bell curve. The standard normal distribution is normal 0, 1, and this is the formula for it. And so that is all for this lecture. So I advise going on to the next lecture, lecture 11.